Hello everyone, my name is Svetlana Minakova and I'm a PhD student of Leiden University, located in the Netherlands. I'm performing research in fields of deep learning and embedded systems. My research is conducted as a part of a European project called ALOHA. In this video, I'm going to present my research paper called Buffer Sizes Reduction for Memory-efficient CNN Inference on Mobile and Embedded Devices. I would like to start with some background necessary to understand the presented research. On this slide, you can see a convolutional neural network. Convolutional neural networks, or CNNs, are powerful, biologically inspired computational models, typically represented as computational graphs, with a set of nodes, called layers, and a set of edges, representing data dependencies between the layers. Due to their ability to handle large unstructured data, convolutional neural networks has become dominant in various computer vision and natural language processing tasks. Due to their high complexity, state-of-the-art convolutional neural networks are typically executed on high-performance platforms and provided to edge devices such as mobile phones, tablets, or cameras as cloud services. However, some of the applications require execution of the convolutional neural networks right on the edge devices. Typical reasons for local execution of convolutional neural networks are data privacy, that requires storage of all data used by the neural network only on the device, or energy efficiency that can be only inferred by specific design of embedded devices. However, execution of CNNs on embedded devices can be challenging. While applications provided as cloud services have virtually unlimited computational resources and memory, the resources of the embedded and mobile devices are very limited. One of the main concerns of local execution of convolutional neural network is their high memory cost that is especially noticeable for mobile and embedded devices that have very restricted memory budget. When a CNN is deployed on a device, it requires sufficient amount of memory to store its parameters, that include CNN biases and weights, and its intermediate computational results. The research I am presenting is concentrated on the decreasing of the amount of memory required to store the CNN intermediate computational results. The intermediate computational results are data produced by every CNN layer during the CNN execution that is stored in buffers allocated in the device memory during the CNN deployment at the edge. The reason why our approach is concentrated on reduction of the size of the buffers that store intermediate computational results of the convolutional neural network is the fact that while for CNNs that were used earlier, such as AlexNet or VGG, most of the memory was taken by the CNN parameters, for more modern CNNs, such as QuizNet or DenseNet, more and more memory is occupied by the intermediate computational results. A number of existing approaches allows for reduction of the CNN memory cost. The most common approaches are pruning and quantization. These approaches reduce precision of CNN data and parameters, and thereby reduce the total CNN memory cost. However, these approaches also reduce CNN accuracy that characterizes CNN ability to solve the task it was designed for. The knowledge distillation approaches replace a CNN with a functionally equivalent CNN of a smaller size. These approaches try to preserve original CNN accuracy. However, since in these approaches a smaller CNN is trained from scratch, these approaches cannot guarantee that accuracy is actually preserved. Moreover, the knowledge distillation approaches are mostly suitable for the CNNs that solve classification tasks and are very hard to be performed for the CNNs that solve other tasks, such as segmentation or object detection. Some of the approaches propose to reuse buffers between neural network computational steps. However, these approaches are not very efficient for the neural networks with residual connections, such as recital nets or dense nets, that should store their data for several computational steps. Therefore, we propose a novel approach for CNN memory cost reduction. Our approach allows to reduce CNN memory footprint without CNN accuracy decrease or CNN training from scratch. Instead, our approach decreases CNN memory at the cost of CNN throughput. Based on the current threats, where the computational power of mobile and embedded devices is growing rapidly, allowing for higher CNN throughput, while CNN's accuracy is increasing very slowly, we believe that introducing a trade-off between CNN memory and CNN throughput is better than introducing a trade-off between CNN accuracy and CNN memory. In our approach, we use ability of CNN layers to process data by parts. On this slide, you can see an animation that illustrates how layers of a convolutional neural network typically process their input data. The example network consists of 4 layers: one input layer that provides data for the neural network, one convolutional layer, one max pooling layer, and one output layer. Every next layer accepts data from the previous layer. The input layer generates an input image for the neural network and puts it in the buffer between the input and convolutional layer. After that, a convolutional layer slides over the image in the buffer with a sliding window and produces output values pixel by pixel into the buffer between the convolutional and max pooling layers. When the convolutional layer is done producing its output data, the max pooling layer slides over the data in the buffer between the convolutional layer and max pooling layer in the sliding window and produces its output values. On the right side, you can see the amount of memory required to store all CNN buffers. For simplicity, it's considered that one pixel takes 1 byte of memory. The total amount of memory taken by the CNN buffers is equal to 76 bytes. As you might have noticed, the convolutional layer doesn't need all input data to be present in its input buffer to start processing it. In fact, it is possible to store only part of input data between input and convolutional layers, which you can see demonstrated on this slide. In the second example given on the slide, the input layer produces data by parts. As soon as the data part is processed by the convolutional layer, the input layer produces a new part of data in the buffer between the input and convolutional layers. The process repeats until all parts of input data are processed. It is important to know that some of the data parts are overlapping. The overlapping data is simply stored in the buffer between the consecutive execution steps. Since only part of input data is stored in the buffer between the input and convolutional layer in this example, the total amount of memory required to store CNN buffers is reduced compared to the previous example. The same idea can be applied to the buffer between the convolutional and pooling layers. On the slide, you can see the third example, where both convolutional and pooling layers process their input data by parts, and the total amount of memory required to store CNN buffers is reduced even further. Recall execution of a neural network, where only parts of input data are stored in buffers between the layers, execution with phases, where a phase is a computational step when a layer processes part of its input data. As was demonstrated in the examples, execution of CNNs with phases allows to reduce buffer sizes by storing only parts of data between the CNN layers. However, it involves overheads related to the increasing number of kernels that has to be executed to perform CNN functionality. Thus, CNN execution with phases involves a memory throughput trade-off that we utilize to ensure memory-efficient execution of CNNs on mobile and embedded devices. There are 2 important requirements that has to be met for CNN execution with phases. First of all, the phases has to be properly defined and ensure that CNN is executed with minimal buffer sizes. Secondly, phases have to be executed in specific order that guarantees CNN functional consistency. To fulfill both requirements, we use algorithm presented in our paper to automatically transform a CNN into a cyclostatic data flow model. A cyclostatic data flow model is a widely used model of computation that has means for phases representation, as is accepted by many existing embedded system design tools. The CSDF model generated via our algorithm properly defines phases for the CNN execution with phases, ensures that CNN is executed with reduced buffer sizes, and is accepted by existing embedded tools that allow for search of proper phases execution order. In particular, in our approach, we utilize SDF for free tool to find execution order of CNN phases for CNN execution with reduced memory cost. On this slide, you can see the experimental results provided for convolutional neural networks from ONNX model Zoo. Every of these CNNs was transformed into a CSDF model via our algorithm presented in our paper and analyzed by SDF-free tool that allowed to find the proper execution order of the CNN phases. As I explained earlier, CNN execution with phases allows for reduction of the CNN buffer size at the cost of the CNN throughput. As you can see on the slide, our approach allows to reduce 70 to 64% of total CNN memory, the amount of memory showed for both CNN buffer sizes and parameters, at the cost of 3 to 54% throughput decrease. It is important to note that throughput decrease percent is typically lower than the memory reduction percent. Before I finish my presentation, I would like to thank DSD organizers for inviting me to participate in the conference. I would also like to wish everyone to stay well in these difficult times. And I would like to remind that the presented research is conducted as a part of European project called ALOHA. So please visit our website if you are interested in our research. Thank you for your attention, and please ask your questions.